Yes, so we are continuing our discussion about the imperfection sensitivity of structures. And we said, if you remember, this is page 126 in the book, and I have sent you, either given to you or sent to you, those who are taking this course on FITS, the copies of these pages from my book. By the way, the book has, of course, a copyright, but since I copied it as an author, hopefully this does not apply to me. But the main thing is that book is now out of print. So Xi we changed into S, and we have this complex plane. And this complex plane is a plane of which has in horizontal axis real part of S, and perpendicular axis imaginary part of S. Now the poles are denoted by X's, zeros are denoted by O's, and this root locus method gives us variation when this parameter of initial imperfections varies from 0 to infinity. When in this equation, which is here 547, 1 plus psi bar psi of S. So when psi bar is 0, then in order this equation to hold, psi of S should have poles, means zeros of the denominator. When psi bar goes to infinity, psi of S should have the 0, and that means 0 of the numerator. Now, therefore, it is very easy to find both zeros and poles, and then see the evolution of the roots. An evolution of the roots, turns out, has some distinctive features. Look, please. I would like you to read material by yourselves. That will appear in the take-home test, because now what happens is that, for example, there are some specific cases that should be differentiated, like a squared equals 3b. Then we have roots going, look please, from zeros to, from poles to zeros. And here also, that means that we have real root. Imaginary part of S is 0. And these roots are positive. You see, that is how, there are also negative roots. This starts at 0 and goes to infinity. And here, double 0 means that there are coinciding roots, two roots. Now, interestingly, Budiansky and Hutchinson of Harvard considered this model and found numerically that a squared equals 3b is a delimiting case. Means that there is one behavior when a squared is smaller than 3b, a squared is greater than 3b. We here find results analytically. Now, an analytic solution usually also gives some additional results. First of all, buckling load versus initial imperfection. That means analytical relationship. And also some additional case. Additional case, A square equals 4B, which they did not detect, even numerically. Even numerically that was not detected. Indeed, A square is 3B is a distinct change of behavior, as I will illustrate. A square equals 4B, some specific behavior, but it's not easy. I mean, look, they are not, I mean, these researchers will not say, okay, A square equals 3B. Then they would say, oh, A square equals 4B, or A square equals 5B, etc. They would not go into this, such a search, such a numerical search. They just found different behavior in different cases. Now, that is a behavior, that is a root locus when A square is smaller than 3B. Now, what happens is, look, here there is this one root, which is minus A over 2B. Then there is another root, which is 0. Then these roots, when initial imperfection increases, come to this point. At this point, look, there is a break and roots are complex. If the roots are complex, that means that after that, we don't have a positive root. We want, when initial imperfection is positive, we want to have a positive root. That means that there is some limiting behavior. This suggests that there will be imperfection sensitivity up to this point, and there will be no imperfection sensitivity after that. This is so-called breakaway point. Okay, these roots change, and then suddenly they coincide. They coincide here, then they are actually split. Interestingly, there are computer programs, I mean analytical computer programs, usually in control courses, which can give you root loci or root locus plots analytically. You can get that. When we did that, that was not available, but now it is available. I don't know whether it's Mathematica, but I think there was some special program for control. I remember maybe 4 or 5 years ago. But most probably MATLAB will do that. Now, that is a behavior, for example, look please. So that is a very interesting behavior, that the same point is 0 and the pole. But here there is one variation when it goes to 0. So it is A smaller than 0, B greater than 0, initial imperfection positive, A square equals 4B. This is a very distinct behavior. When it is 4B, then 0 and pole coincide with each other very interestingly. And then there is another case where A square is between 3B and 4B. In this case, we do have this positive root availability. So now what we are getting, what is the conclusion? Conclusion is written here. For the case A square greater than 3B, there are always two real positive roots, to phi of psi equals 0, and the structure buckles. Consequently, the structure turns out to buckle for a square greater or equal than 3b. In the range a square smaller than 3b, structure buckles only if initial imperfection is smaller than some critical initial imperfection. And this critical initial imperfection, I find it analytically. I will write it down for you. Just write this first sentence. And this critical initial imperfection is written here, equation 545. Initial imperfection critical equals minus a square over 9b, 1 divided by 3b minus a square. Because a square is greater than 3b, this is a positive quantity. So you can write here on that page 548. So here you can write down given by equation 548. Now when it is greater than 4b, this is figure 518. Now, this behavior can be seen here. Look, that is a sample point. Look, please. That is figure 512. Look, please, here. You have imperfection sensitivity when initial imperfection is small. But when initial imperfection is big, you have no imperfection sensitivity. It goes just monotonically. So this transition point is given by critical initial imperfection. Indeed, in life also, very small deviations, of course, affect behavior badly. But sometimes very big deviation from some rule gives another equilibrium state totally, which has no connection at all with imperfections. Okay. You may want to describe cases by yourselves. And now, the equation itself, this analytical equation, is here when we have both A and B. And that is given by equation 550. Okay? That is 1 minus, let us see that. Okay? So that is 1 minus lambda static over lambda classical minus a square over 3b cubed equals minus 27 fourths b. You don't have to write this because you have it. A over 3b, 1 minus lambda static lambda classical minus 227 a cubed over b square plus lambda static lambda classical initial imperfection squared. Now we would go to something what to do now with these formulas. So these formulas gives us a connection, lambda statical over lambda classical, as a function of initial imperfection. Now, and this is analytical relationship. Now, very few analytical relationships available in the literature. Okay, for which structures? For models one can obtain, yes? Even for this model, we had to work quite hard, and not until relatively recently these formulas were obtained. Now, interestingly, for shells themselves, results were obtained by W.T. Koiter, some analytical solutions, 1945, that is his PhD dissertation, and 1963 paper. We were very happy to obtain some analytical solution also. Koiter, Elishakov, Lee, and Starnes for the shell which has initial imperfection, but also thickness is non-constant. So here he has thickness constant. Here thickness non-constant. But usually there is no analytical solutions. There are thousands of numerical solutions. So what kind? That is a question. So what they say is as follows. Papers start as follows. Let us consider a shell with the following initial imperfections. And then they write a formula. For example, W prime, okay, Xi prime equals, for example, 0.0012 plus 0.0134 cosine 2 theta times sine 6 pi x over L plus 0.02975 sine 3 theta sine 7 pi x over L. For example. What is your question? Student asks, student. Do they really do so? Reply, yes, indeed. Now, that is not a trivial observation, because to do numerical analysis, one needs input. So input is taken as the analysts please. Because they say any assumption is as good as any other assumption. Any other assumption. Let us take this. Okay? They actually say, I, a numerical analyst, prescribe initial imperfections, prescribe two initial imperfections as my servants. to be this. Okay, that is what they say. But they are, I mean, okay, we don't want to say that these numerical analyses are not clever. We are not criticizing them. You have a computer program. Computer program is something which needs an input. He developed a computer program. So the question is, what kind of input should he take? So he takes, for example, this input. I will tell him, no, this input is not good. So he will tell me, give me your input. This input is not so good. Okay. Give me your input. Do you have any questions? Suggestions? Can you participate in the discussion, Mr. Rollo? I don't want you to sleep here.
I wonder why you didn't take an easier interpretation.
Oh, easier. Okay, why not? Look, if I have a program, general program, I can assume a complex of representation. Certainly it will work if I have a simpler representation. That's no problem. You can take, for example, you can take alpha here, beta here, then put alpha and beta equals 0, then you have a constant, or gamma here, and then you can have anything you want. 3 of them, or 1 of them, or 2 of them.
But usually we first begin by is the restriction model, and then you get more complex.
Yeah, of course, this is in the paper already. Of course, they start with the easier cases. Then they go further. For example, what they would do? They will take the same imperfection as Koiter had in his work for analytical solution. They will get results which are close to Koiter's, imagine. Then they will develop a more general program, and then to test it, it sounds fair to give a complex representation. Okay.
Because, of course, I can always say, okay, this model is not correct, let's consider another model, right? But I don't want to go into details about cosine beta or sine beta, whatever the analytical function. I'm just wondering about the influence of these numerical coefficients.
These numerical coefficients influence the answer, of course. But they say, whatever you will give me, I will calculate the answer. For this input, that is an answer. It's very fair. Means he took this input, he will give his answer. Because he has to put some numbers. You don't like this small now, he can write 1, he can write 1, 2, 3 here. Will it be better for you?
No, I don't care about that.
Okay.
Of course, I mean, every time they change the number, they will get a different answer.
Certainly, but that they have a general computer program. For example, the same happens in analytical calculations. Sigma equals P over A. When you change P or A, you get different answer every time. It's certainly. Or area of the circle, pi r square. When you change r, you will get different area. It's very natural. You want to get the same area and you change radius. No. Any other questions? Mrs. Piert? No questions? Mr. Espinoza? Again, Mr. Zingales? Of course, they can.
They perform numerical analysis for every time with different numbers.
Again, you don't understand what I'm saying, I think. You have a basic misunderstanding. I'm answering Mr. Zingales. He says there are thousands of shells. They don't consider thousands of shells. They consider one shell with this imperfection. And if you will change the numbers, they will get another result. If you want 1,000, why 1,000? Maybe 2,000, 3,000. Yes. Any other questions? So results are directly a function of the specified imperfections. But then there is a feeling of unsatisfaction, because actually a real shell seems to stay away. Okay, there is not this given shell. I mean, so one can do as follows: reality, real shell. One can take a shell okay, that is a shape. Real shell. Take a real shell and measure imperfections. And such devices are available in many places to measure imperfections, like Caltech. Caltech means California Institute of Technology. Then Braunschweig, DFVLR. That is NASA of Federal Republic of Germany. Then Delft University of Technology, etc. Then Belgium. Then Israel Institute of Technology. This is University of Ghent. They pronounce it Ghent. Extremely beautiful city also. There are so many perfections that they can accommodate some imperfections in shells. Okay, so in some places. So they can, for example, I'm showing you just this shell, for example, in the machine. Okay, this is a shell. Okay, that is the shell itself. Okay, that is in the buckling test. But there is this measurement apparatus here in figure 2.3 of the book. Okay, this is the shell. Okay, here is the shell. And there is a possibility to measure these initial imperfections. Then, for 5, measure imperfections means that, say, we measure psi bar as a function of x and theta. So that is a shell. So this is x, and this is theta. And one can put then, look please, these initial imperfections are known, psi and theta. Then you put it in the computer code, get buckling load, lambda static over lambda classic. Now, 1949, Nicholas Hoff says, shells which produced by the same manufacturing procedure, two shells produced by the same manufacturing procedure, have different imperfections. The shells can be cylindrical or spherical, etc. For example, when you go to Publix next time, you just can look two apples. Take two apples there, or some apples. You can consider them to be actually spherical shells. You will see that they have even, there is some control mechanism, interestingly, in the US Publix. They are not putting any apples, but apples of of nearly the same size in order to charge us a bit more, or maybe much more. So you will see that the surfaces are different. So there is this scatter in the surfaces, okay? Maybe, I think that I just inspected very most recent time, different apples, and I found that Fuji apples had less or least imperfections. But when I was inspecting them, I was just looking around so that they would not say, what this person is doing, looking at this apple and rotating them, in a strange manner. What this person is doing with these apples? And he's not buying them, does not put them. I mean, I put maybe several, but then I'm inspecting and choosing and looking. They did not ask me anything. Say it again? Okay, student is asking an apple to be brought to him, I mean to us, to students. But I did not want to discriminate, feed students. So that is why I did not bring two students here. Okay. Now, 6. So Nicholas Hoff says that we need to use probabilistic methods to describe scatter of imperfection profiles. So that was 1949. So Nicholas Hoff just gave an idea and did not realize it. 1958, V.V. Bolotin published apparently the first paper that described imperfections as random variables. Okay? Then 1969, so Bolotin is from former Soviet Union. Imperfections in that country was so big that country ceased to exist. 1969, Budiansky and Fraser, okay, that is his PhD of Fraser. He's from Australia. Published a paper where they dealt imperfections as random fields. Okay? So these are two milestones. Means random fields means like entire functions. Okay? So these two approaches were bridged by Monte Carlo method. That was 1979 by Your Obedient Servant. And other papers. So this works. Okay, maybe I will just describe very small why I got interested in this, but I will be not discussing this at large. Actually, 1965, Bolotin went to US, to Harvard in particular, came back and told to his PhD student, Makarov, okay, do as best as you can to surpass anything done at the Harvard University. So that was his, I remember I was there, I was standing there, I heard this. But that is not interesting. The main interesting, that is an interesting fact, so that is what you should try to do. But my interest was different. Budiansky and Fraser obtained 1969 the following result. Imperfections are different, they are random, but for the infinite structure, the buckling load is a deterministic quantity. Means buckling load does not change. Look, as I said, we have a program, computer program. You put imperfection, you get a buckling load. You put another imperfection, I hopefully get another buckling load. If you take psi j, you will get lambda sj. But they obtained that it was not changing. So I found that to be paradoxical. And I thought, okay, let us start with doing experiment. Let us forget now their analytical experiment. Experiment in computer by Monte Carlo. So then we had to simulate fields. So that was 1979. I gave a method how to simulate random fields. And then already did other things. But now we are not going, that was my interest. It has nothing to do what was told to Makarov by Bolotin. You should do best to surpass or something. That was his job. But my job, which I described to myself, was to understand this paradox. But I'm not going to talk about paradox. Let us talk about some randomness. Probability. And I should say it while I'm actually standing on one foot actually, okay? So imagine that the second foot the person is holding, I'm discussing it within several minutes only. Okay, so probability, theory of probability. Theory of probability was developed by two Frenchmen who had a rather inactive lifestyle. means did not travel. And that is Fermat and Pascal in their correspondence. They corresponded with each other, wrote letters back and forth. French post was quite reliable, and they developed the theory of probability. Now, the main idea of the theory is so-called probability density function. And this is a function, say it is called f, that is random variable a, and that is x, this is x, and that is this function f. That is a density. Now this density has a very interesting property. It says that if you take any value, say alpha and beta, and then you integrate this curve, this density, between alpha and beta. So integral of f ax dx between alpha and beta is nothing else but probability that a takes values between alpha to beta. So that is this density. This is, okay, 9. Not unlike the mass density. Now, what is mass density? If I have a wire of a varying density, say a rho of x, that is a mass density, then I can take, for example, connect this with coordinate system. Then that is 0. And then take alpha and beta. Then then integral of rho x dx between alpha and beta equals mass between points alpha and beta. So here then, the integral of rho x dx between, say, if this is minus infinity to plus infinity, equals entire mass. Okay. For example, if this is an apple, for example, which is by chance we transferred it into some wire, then you pay, they are weighing it, and you pay according to the mass, according to the final mass. Okay? Now, for probabilities then, so what is the integral of f a x dx between minus infinity to plus infinity? That is a probability that x takes values between minus infinity and plus infinity. So we say that such a probability is that random variable takes values between minus infinity to plus infinity is certainty. And we are saying that it equals 1. For example, if we were a country of high inflation, we could have assigned value, for example, 1,000 or 1 million or 1 billion, etc. For example, it will be interesting, for example, to say to your mom that with probability of 1 billion I will take the garbage today. That sounds a bit more convincing. Rather than to say with probability of 1 I will take garbage today or something like that. It depends. Anyways, it's an assumption. We are saying that the certainty is associated with 1, but it could be anything actually. But it's easier to deal with the 1 than, so many zeros. You can forget the zeros. The secretary is typing. You can add zeros, subtract zeros. Yes. So, now, once we have this probability density, we can calculate probabilities. We can calculate various probabilities. Now, so that is the main thing, main idea actually. See, we don't need even this person to stand on 1 foot. I mean, he can even stand in quarter of a foot or something like that. It's very simple. I explained in 1 minute, actually. The entire theory of probabilities, main idea. Now, let us look as follows. Look, please. We have connection of initial imperfection. Look this. That is this. Let us take a symmetric structure. A equals 0. B is smaller than 0. Then so this relationship is what? 551, and that is given. 1 minus lambda static over lambda classical 3 halves minus 3 square root of 3 divided by 2. Initial imperfection absolute value minus b lambda static lambda classic equals 0. So that is this relationship is depicted here. So this is actually lambda static over lambda classical, and that is initial imperfections. Now here I will depict underneath probability density. Imagine probability density is like this. I don't care. So that is f of initial imperfections. That is initial imperfection. And that is initial imperfections value. So that is given. So this is obtained from experiment. Hopefully, okay? We hope for the stochastic analyst that he obtained this from experiment. Now the question, the main question is what kind of question to ask? That is a question. Okay. I have this relationship and I have this density. What is a question I could ask myself? 11. So Mr. Zingales, he says, I can ask for probability density of lambda static over lambda classical. Question, what will you do with this? Okay, do we have any other questions? Can you ask any other questions directly, what you want? What you want? What is a kind of question we can ask to calculate? We already heard one answer. Okay, the question which we ask, look, now we can ask following questions. Question 1. Okay, let us think what kind of questions. Imagine that you are working in this firm. And interestingly, why I'm saying, assume you work in a firm. Actually, Mr. Roland will be working in the French, or for the French nuclear power authority, and doing research for nuclear power plants in conjunction with imperfections. What should he think about? What should we recommend him to think about? Now, because he is going to work and we are not going to work there, so we are as laymen. That is the question. I'm a layman. What should I ask Mr. Rollo to think about if he is going to deal with nuclear power plants? Mrs. Pierre, please be more active. What would you want as a citizen, as a layman, as a lay person? Can you speak louder? Say what you think and tell.
The question one more time, I'm sorry.
Again, imagine that we are discussing with Mr. Roland his plans in France. And actually that is what he will tell you. He says that he is going to work for the French Nuclear Power Authority and doing research for nuclear power plants in conjunction with imperfections. So what would we want him to think about? Safety, you say. Okay, Miss Pierre says safety. Safety. So question, what is safety? What do you mean by safety? What do you mean by safety? I mean, safety is just one word. How to explain it to a person? Imagine you are on TV now. You are an engineer. You took my course. You say, oh, we would like Mr. Rollo to think about safety. The journalist says, what do you mean by that? What do you mean?
Sure that the nuclear power container doesn't buckle.
Oh, make sure that is where I wanted, that is what I wanted to extract from you. Make sure, she says, that the nuclear power plant container does not buckle. Yes, that is what you said. That is her desire. Now, journalist. What is the question of the journalist? No. What will clever journalist ask? Not what is a buckling, because he has a very short time. He has 5 minutes, with Mrs. Pierre. So, no, not how to shoot. Is this possible?
How to be sure what I said.
So, is it possible? Again, no. Make sure, she said, that the nuclear power plant container does not buckle. That is what she said. When you say, for example, some statement, the first question that should come to mind, whether whatever you want is possible or not. Is it right? For example, when you come to the course, you cannot ask, for example, to get a grade which is 200. The maximum you can get is A. You cannot ask to get AA, for example. That is an impossibility. Just an example. So, is it possible container not to buckle? Let us look here. That is this form. This is this graph. This is a buckling load or limit load. This is imperfection. Negative imperfection or positive imperfection. So what should Mrs. Pierre answer the journalist? She should say that it is impossible. Because for every imperfection, I have a buckling load. For every, and certainly my imperfection, which I have there, and I do have there imperfections, there will be a buckling load. So we should say that make sure that the nuclear power plant container does not buckle this is impossible. That is what I wanted to discuss with you. That is an impossibility to ask there is no buckling. Because as we said, we have a relationship for every imperfection, we get this buckling, and there is this formula. Look, any imperfection you put here, you will get lambda statical, lambda classical. And, you will get this relationship. It's very trivial. So that is not possible. Now, when journalist, if this is impossible, I think that is what clever, then what should we as, okay, continue. That was a hint.
Assume.
As public desire. Because look, she said, make sure that the nuclear power plant container does not buckle. That is a very maximalistic requirement. This maximalistic requirement cannot be met. Okay? That is a too maximalistic. So the question is, what is not too maximalistic? Is it right? That what I can demand, look, please, you have a house next to this nuclear power plant. You better demand maximum, especially if they are asking you, before they are constructing it. So what should we now journalist is not a person who knows everything, all I know, and you are just, so to say, now you have a time to educate this journalist. Okay, if it is not, then what should we as public desire answer?
As maximum as possible.
As maximum as possible what?
That our nuclear container
So lower risk? There is a risk.
As low risk as possible.
as low risk as possible.
Means that if there is a buckling load, then this buckling load should be as how? Which one? So for any initial imperfection, there is a buckling load. So what kind of, there is no possibility that there is no buckling. So what should we demand? We should demand actually that buckling load will be very high. Is it right? Buckling load will be very high, or limit loads to be high. Very high. That means, for example, if I'm let us specify some load lambda star. We want no limit load, we want limit load to be not less than lambda star. That means that we want nuclear power plant not to buckle prior to lambda star. This is not unlike we want person not to die before certain age. We cannot ask immortality, but we can ask, so to say, not to die before certain age. Is it right? 13. Not unlike lifespan. We cannot ask for immortality. I mean, we can ask, of course, but probably it's not easy to get. Is it right? But to live beyond certain age. Okay? So we want structure not to buckle prior to some buckling load. So that is what we are getting at. You see, I try usually not to communicate to you ideas, but to uncover ideas together with you. So I'm taking some lambda star over lambda classical. And I want, if I have to buckle, unfortunately, I want to buckle beyond this value. So I want to be here somewhere. Okay? If the power plant has to buckle, let it buckle beyond lambda star, which I specify. Okay? I would like to ask to bring me a paper because I think we are out of paper. Now, he will bring it. So, if this is the case, then these are the initial. Now the question is, how to buckle beyond this? Means that initial imperfection should be here. If initial imperfections will be here, then buckling load is there, and this is here, etc. So if it is lambda star, then it is very easy to get these values. Look, please. So this is psi bar, yes? Absolute value of psi bar equals, from here, 1 minus lambda star over lambda classical, 3/2, divided by 3 square root of 3 over 2, square root of minus b, lambda star over lambda classical. Okay, that is this value. So it's minus and plus, here and there. Okay, so I want to be in this region. That means I want to have a probability that lambda static over lambda classical to be greater than lambda star over lambda classical. Of course, this is a function of lambda star. This depends upon lambda star, such a probability. This probability is called reliability. Mr. Zingales has some probabilistic knowledge, and he did use this word reliability, but I was unable at that moment to extract more basic notions than reliability. See, sometimes you know the subject and you may anticipate what should be done, but basic steps, how to explain why we need that, is very difficult for him to give. Okay, reliability. Now, so this reliability, let us denote it by R, and that is a function of lambda star, of course. So we have R lambda star equals probability that lambda statical is greater than lambda star. So that is the reliability. That means like life beyond certain age. For example, in last century, I think the average age was 35. And in this beginning of the century was 45, etc. is 75. or 76 in the United States, I think. So a person wants to calculate probabilities that his life will be greater than maybe 80 years old, etc. Of course, more you get to that age, its probability is greater to live closer, is it right? When if you are 79, the probability is greater to live till 80 than you are, etc. Now, if that is the case, then it is very simple. Reliability of at lambda star equals probability that initial imperfections are between, as we said, I calculated this, 1 minus lambda star over lambda classical, 3/2, divided by 3 square root of 3 over 2 square root of minus b lambda star over lambda classical, and here is minus the same quantity. Now, we already know that if I know the density, then it is very easy to calculate. That is f initial imperfection psi bar d psi bar from minus, okay, I'm writing now, 1 minus lambda star over lambda classical, 3/2, 3 square root of 3, 2 minus b lambda star lambda classical. And here is the same with plus. 1 minus lambda star lambda classical, 3/2, 3 square root of 3 over 2 square root minus b lambda star over lambda classical. So that is R of lambda star. So you have to just put this function. Okay, once you put this function, you will get the appropriate result. Please write this formula. And I will give you a homework if you don't mind. Okay, I will give you an assignment when you come to my room tomorrow, okay, if you don't mind. Because I took too big a book, Continuous Univariate Distributions, Volume 2, etc. I should find the I will give you an assignment, but these materials and so that is actually falling in the category of stochastic stability. And the results will be in this research, as well as research about shells of various kinds, let us say. Will be in a forthcoming book that is by myself, E. Wei Li, and J. H. Tarnes, Jr., non-classical problems in elastic stability, deterministic, probabilistic, and Anti-optimization approaches. Cambridge University Press, New York, 1999, hopefully. Thank you. Now, just one more thing I can give you.